I like to thank the organisers when I start, because otherwise I forget. So thanks to the organisers, and it's a great pleasure to be here today. Yeah, as you've heard, I'm going to be going in a different direction. I come from the Green Chemistry Centre of Excellence, and we look at chemistry and how we can use what we currently consider waste to be, and how we can use that as a resource rather than just throw it away. So to start with, just a quick introduction to what green chemistry is, because I appreciate this is an audience where there's probably very few chemists. And then talk about one of the main areas we're looking at now, which is food waste and biorefining, and then towards the end, some phytoremediation, so how we can clean up land and actually use it in a chemistry context. So green chemistry was first defined about 25 years ago, and at the time it was really looking at chemical processes and trying to make them more efficient. As we heard, Siemens factory is about 80% efficient or 80% inefficient, I think, is that the one?
Inefficient.
Yeah, inefficient, yeah, that's way better than most chemical processes. In terms of resources, most chemical processes are probably 2 to 5% efficient, and some are considerably worse than that. It's quite astonishing. So that was started off looking at how we can improve the efficiency of these processes and how we can measure the efficiency better. It then began to look at lower energy use, because chemical industry is a big energy user. It looks at safety, but it's begun to expand into things like end of life. So what happens when something's finished? What happens when this computer stops working? It probably just gets sort of thrown away. It's full of very useful materials, very useful chemicals that we potentially could get back, but we don't, because we don't think about it. We just buy another one and off we go. And that then begins to move into a more circular way of using materials, and where we've really been working a lot is sustainable feedstocks and how we can use them far more efficiently. So looking at food waste, this is probably a little bit small, but the bottom line is there's a lot of it. So annually there's about 1.3 billion tonnes of food is wasted, which is quite a bit. That's 200 kilos for each of us. So that's about a dinner a day. It just gets flung away at some point throughout the supply chain. Whether it's supermarkets thinking that tomato isn't tomatoey enough, or that pepper isn't quite perfect enough, whether it's the wrong amounts of stuff being in the wrong place at the wrong time, whether it's us throwing stuff out because, like me, you stick it in the oven and forget, whatever. There's huge amounts. There's also about 3 billion tonnes of inedible waste, because most of the plant you can't eat, and that's a very underused resource at the moment. And that's really the areas that we've spent most of the last 15 years working on. And what I want to do is just give you a few examples of that. So if you look at food supply chain residues, you can extract a lot of things out. So you can just pull out a whole range of different things, some of which are already used. Pectin is used obviously in the food industry a lot. There's amino acids, cellulose, a whole range of different things, phenols, sugars, etc., etc. And then you can then convert these into a much wider range of different products using clean synthetic methodology, using catalytic systems which are trying to improve the energy efficiency. And one of the things is we're trying to move away. The chemical industry essentially uses crude oil as a source for pretty much all the chemicals it produces. It produces 100,000 or so chemicals a year, many of which we use without knowing about it. I'd be surprised if 1% of those were naturally based or sustainable. So trying to move away to produce the same chemicals or equivalent things that will do the same job from sustainable materials is a big challenge. One of the things we've had quite a lot of success with recently is what was named by one of the students OPEC, try and poke at the oil industry. And it's really trying to show that orange peel, so that there was orange juice over there, I'm not sure if it's still there. You squeeze orange juice, you squeeze an orange, 50% of it's thrown away. That's the residues, the peel and the internal bits and little bits of juice and so on. And that, nothing much happens with that by and large. What we've done is we've taken it and we've microwaved it under various different conditions. And we've got a range of different products out of there, each of which are, at least in principle, usable. And we're working with a range of companies to actually exploit these things. And what you can find is that most of it is actually useful. We throw it away, but we could actually use it if we put our minds to it. Why do we use microwaves? As you can see, they're not domestic microwaves, but they give what's called volumetric heating. So they heat the thing you want to heat. Conventional heating heats the thing that's contained in it, that heats the container, and then the container heats the contents. So it's slow, it's energy inefficient. If you have to stop it heating, you stop it heating, but it doesn't stop immediately because the container is hotter than the contents. The microwave's the opposite way around. It heats what's inside the container, it doesn't heat the container. So you switch the microwave off, it cools down. And in terms of safety and chemistry, that's a big thing. It also means you're not heating 2.5 tons of steel because you want to heat 200 litres of something inside it. You can do continuous processing, works with a range of feedstocks, and it allows the use of wet feedstocks. It's actually ideal if it's wet because water is the best, or one of the best microwave absorbers. So we take our wet orange peel, 80% of it is water, and we heat it in the microwave at just under 100 degrees, and that actually drives some steam off. So most of the water comes off there, but it also takes limonene, and it's really quite effective. And limonene is very good. Flavour and fragrances use limonene or not. It's what makes oranges smell of orange. It's used in the electronics industry, so if you accidentally eat your phone, it will taste quite nice, I suspect. I don't really know, but I think it may be used to clean things. It might be used as a solvent. But, and it's also used as what we call a platform molecule. So chemically, it's relatively complex. There's a lot of bits in there you can play with. You can actually make a lot of other stuff with it. Moving on from that, you then have a residue. And the residue you can then extract, and that gives you flavonoids. And the flavonoids have got quite a lot of biological activity. They're very interesting for a whole range of reasons. So you can wash them out quite easily, and they come out more easily after the first microwave thing, because the microwaves actually are good at bursting open cell walls, and that releases the contents quite nicely. You then get another residue, and then if you ramp up the temperature again to 120, 130 degrees, you can get pectin out. And the pectin we get out obviously goes into food. It's what sets jams and marmalades and stuff, but it's also used as a thickening agent in cosmetics, and it's used as a component of things like tablets and pills and so on, as a sort of gelling agent, and a sort of matrix for the active ingredient. So that comes out, and this just happens going through a continuous process, going from one vessel to the next, and the temperature just gradually ramps up. And at the end, you have cellulose, and there's two things you can do with the cellulose. The first thing is you can convert it to bioethanol. Again, microwaving at 190, you can actually break that down to sugars. You can then ferment the sugars, and that works quite nicely. Or we're interested in trying to find other uses, because the microstructure of the cellulose is actually very different to normal cellulose, and there may be other things we can do there. So we're commissioning a semi-continuous microwave that will go through the whole process and get out all these products. We've got patents, and we're working with 5 or 6 different companies for each of the different products, so trying to build outlets for all these different things. Another thing that's come out of a similar thing, again from waste cellulose, is a new solvent, styrene, which is a combination of us and Circa, who are an Australian solvent manufacturer. Solvents are one of the biggest products in the chemical industry. Most chemical processes use a solvent, and most of them, probably 90% of the contents of the vessel is a solvent, so it's a big, big thing to get right. Some solvents are really pretty nasty, pretty toxic, under a lot of pressure to be banned. One of which is NMP. Very widely used. It's actually just very, very good at what it does, but it's really pretty nasty stuff. And styrene is molecularly really quite different, so it's much less toxic, and it does the same sort of things as that does. So this is something that you can take from cellulose and replace it in many, many systems. So again, that's another outlet for the cellulose side of things. Again, looking at coffee grounds, another thing that is generated in substantial amounts. And this is a project we did with a small community group in York, St Nicholas Fields. They're a group that took over a park that was kind of derelict. They took it off the council's hands, and they've started developing it and cleaning it up, and they use it as a community resource, so schools come in and learn about the environment and learn about ecosystems, etc., etc. And you know, we occasionally go along and volunteer and help clean the place up and mend fences and all this kind of stuff. And we got talking, and they were actually collecting coffee grounds just as a sort of mulch that they used just to put in the ground from a cafe. And we said, well, why don't we look and see what's in them, see if there's anything else we can do with them. So what we did is we found an easy way to extract the oils out of the grounds. We also found a small specialty soap manufacturer who can use those oils, so they put these oils into soaps, which they then sell. And then the residual grounds go to another small company, Fungi Futures, who grow oyster mushrooms on them. And then they go on, then the residues go onto the ground afterwards. So the residues still do what they did before, but you've got 3 or 4 other things coming out of that as well. So that was quite a nice little thing, and that was a waste velour project we had, which was designed to bring in lots of different companies and try and interact with them, often in very short projects. And that was very successful. Another big thing we're looking at is something we call starbin, which we get quite excited about. Probably more than we should sometimes, I think. But anyway, it comes from starch, but which is a big waste material. There's lots of waste starch around. It can also come from pectin, so another outlet for the orange peel stuff. And it can also come out of alginate from seaweeds. So the starch we can make into a high surface area porous material, or mesoporous material as we call it, which is great for catalysis, it's great for adsorbency, and we can then pyrolyze it, and the word starbin comes from starch and carbon. So you partially carbonize it, and you've got something that's got some starch characteristics and some carbon characteristics, and you can tweak the balance. So you can make it more carbon-like for some things, more starch-like for others. And that's something we use for a whole range of different systems, going from catalysis to batteries to a whole range of applications. So for example, precious metal from waste streams, it's very good at absorbing some precious metals. Purification, it'll absorb organics from water, it'll absorb things like formaldehyde from air, which is a big problem. Various analytical applications, and then as catalysts as well, so we can catalyze a range of reactions with it. So potentially there's a lot of outlets for this material, and it can be used from waste materials. Moving slightly away from what most of us in the West would call food waste, because not many of us eat a lot of seaweed. We've been looking at Ascophyllum nodosum, and that was a small company in Shetland that we worked with there. We now work with a company in Uist who do the same sort of stuff. And what they do is they squeeze the seaweed out and they get a juice, as they call it, which is a great fertilizer for plants and so on, and you see it in grow bags everywhere. But they end up with an awful lot of what they call grouts, the residues. and there's not much being done with these at the moment. We've looked at it, and again we've gone through the same sort of process using microwave chemistry to do a range of extractions. So you can extract fucoidins, which have got very interesting biological activities, alginates, which go into the food industry and various other things, and sugars. So you can get 3 different products out from there, and you can convert the sugar through to bioethanol reasonably efficiently. You end up with a residue which we call biochar, which is degraded sugars and other bits and pieces, which is a reasonable solid fuel. It's not fantastic, but it's not too bad. So again, you can do a stepwise extraction and deconstruct the material and find value for quite a lot of the components. Very briefly, chitin is one of the main components of seafood waste. It's part of the shell structure, and it goes into a whole range of things. This is something that's been going on for a long time. It goes into contact lenses, wound dressings, a whole range of things. So again, it's a way you can valorize what is otherwise a fairly substantial waste stream. And again, one of the drivers here is that waste disposal is actually becoming quite expensive. So there's a financial incentive as well. So the last thing I want to talk about is elemental sustainability. So everything up to now has been carbon, and everyone's been obsessed with when's the oil going to run out and peak carbon and all this. And what people have forgotten is we use a lot more elements in the periodic table, and quite a lot of them are under threat as well. So for example, indium is a classic example. Indium is in most flat screen devices. It says there 13 years remaining supply. That's probably 5 or 6 years old, but everybody keeps saying 13 years, so whether we keep finding little bits, I don't know. But nonetheless, we're going through it at a fair old rate. There's not much left. Various others, germanium, neodymium, hafnium, there's loads which are a few years left. There's quite a few as well of the yellow and the orange ones, which look like there's quite a lot left, maybe 50, 100 years. The problem with some of them is that that's 50 or 100 years because we use almost nothing. If somebody comes up with a smart new process, suddenly that might be 5 years overnight. We don't know. So what do we do about these things? And as I say, we throw these things away. The indium in here is far, far, far purer than the stuff we get out of the ground. So theoretically, it's far more sensible to get it out here than to go a mile underground and lift stones up to the surface, grind them up, etc., etc. And one of the amazing statistics that you find here is that 3% of the world's electricity is used in grinding rocks to get metals out, which is astonishing. And it's there. It's relatively pure. There's probably 20% purity in the components that's there, as opposed to a couple of parts per million. But we still dig out the ground. So one of the things we did, we work, and we're working closer and closer with our biology colleagues, using plants for environmental cleanup, and they've done quite a lot of work decontaminating ex-military sites, which were maybe TNT and the like is leached into the soil, and they've got plants which will actually eat TNT and break it down. But they actually pick up metals, and some plants pick up metals really quite efficiently and quite actively out of the soil. And one we focused on, largely because as a group that originally was based in catalysis, palladium is very interesting. How am I doing?
You're doing fine.
Great. Good.
Sorry.
Thanks. Palladium is very interesting from a whole range of things. It's a very good catalyst for a load of different processes. One of the things is it's in catalytic converters in cars, and that means it's distributed very widely. So unlike indium, which is all we know where it is, palladium is now everywhere in very low levels, because it gradually drifts off the catalyst as you drive your car around. So we looked at palladium, and we've been doing stuff, it's only lab-based at the moment, but getting plants to absorb palladium, and then we're trying to convert them into catalysts. So the chemical industry uses a lot of palladium catalysts, and the palladium is on carbon, and they make the carbon from plant-based material of some description, and then they put the palladium on it. So we want to turn that around. So, for example, 170,000 kilos was used in 2010 for catalytic converters. That number's probably drifting upwards. Oh, didn't realise it was animated. Nice surprise. Yeah, so that can spew out several hundred nanograms every time you drive a kilometre, and you drive thousands of those a year. Goes into the soil, goes into the dust, goes into the grass, and it goes into runoff water. So what we wanted to do is we wanted to make catalysts, so not just absorb the stuff in plants, so you plant things and they soak up all the palladium, but to actually convert it into something useful at the end. So we did this in the lab using hydroponics, so essentially just soaking plants or growing plants for 3 weeks in the presence of a palladium source. And as you can see from the pictures there, they do really well on it. They actually don't like it very much, but we're forcing it very hard. I mean, if you're growing it in the soil, there'll be far less palladium there than there'll be other stuff. So we're quite confident it works. But if you look in the bottom pictures, the little black dots are where the palladium's been grabbed by the plants and concentrated into nanoparticles. And these are actually perfect for catalysis. This is exactly what catalyst manufacturers want. So we take that and then we just carbonize it, and the metal particles remain intact, and the plant turns into the right sort of support for them. And the sort of applications, we haven't done all of these, but we've certainly looked at 3 or 4 of them, and they work just as well as conventional catalysts, just as well as the commercial ones. That's loads of time. Great, thanks. But we've extended it to look at gold, copper, nickel, zinc, selenium, titanium, aluminium. They all work really quite nicely. What happens when we go to real case in a real soil and there's half a dozen different metals is a little bit more unpredictable, but that's the next stage of the process to see what the selectivity is and whether we can get individual things growing or whether we get mixtures of stuff. But nonetheless, these things are potentially usable, so you could plant a load of stuff, harvest it a few times, and clean up the soil a little bit, and maybe get some quite valuable stuff out of it. So just to finish off, hopefully you can see there's a huge amount of potential for converting waste to products. We work with a lot of organisations, one of which runs most of the bin lorries in the UK. And 10 years ago they were a waste disposal company. Their strapline now is resourcing the future. So they're beginning to turn things around as well, which is nice. Waste is a resource. There's nearly always something you can do with it. And it's kind of changed the mentality. We've got very lazy since we got oil. We just throw stuff away and keep going, and we have to in some ways get back to where we thought things actually really do have value. But it does open up things. You need well-designed processes to collect. I was chatting earlier and we were saying we had a project looking at glycerol, which was a waste product from biodiesel formation, but potentially a very useful chemical. And because it's a waste product, because it's waste, it gets dumped in a tank, but anything else the producers don't want gets dumped in the same tank. So you get your waste glycerol from them, and you can barely find glycerol in there. You find everything else, sandwiches and all sorts, but and then until they look at things and think, well, this has actually got a value, let's put it in a tank of its own and it'll be a bit easier to work with. That's a big step, and we've done that with a local producer who now have their waste glycerol is now 80% glycerol. When we started working with them, it was about 10, and the other 90 depended on what day of the week it was, and that makes life very difficult. So that's now much more consistent and much richer. And that was quite nice. That was basically putting in another pipe about 3 meters long. That's all they had to do, but they did it and it was good. So the valorization side and the biorefining just because if you don't biorefine, you just take you skim a little bit off your waste, and you've got pretty much the same left as you had when you started. So you really need to do the whole thing, and that again leads to issues because, as I'm sure you know far better than me, the economics of having 4 or 5 interdependent products can be a little bit challenging sometimes, but it's a challenge we have to get to grips with. So that's all I'd like to say, so thanks very much.